The metallic character will affect the melting point and boiling point. So how are we going to know whether an element is metallic or not? It is when the easier it is to remove electron from an atom itself, the more metallic the element. So when we are going from across the period from left to right, the metallic character will decrease because in periodic table we have group 1 and group 2, which are the metal itself together with the traces of it in the p block. Okay, so we are going from left to right, which is from metal to non-metal elements in periodic table. So that's why the metallic character will decrease across the period. So the other name from group 1 is alkali metal, and group 2 would be the alkaline earth metal. So these two are metal. So they tend to form cation, okay, because they tend to donate. Okay, remember back in chapter 2 when I said that when the valence electron is 1 to 4, the element will tend to donate. For group 17, you know this, it would be called as halogen, and group 18 as noble gas. So group 17 and group 18, they are known as non-metal. So they tend to form anion. Okay, means they tend to receive electron in order to achieve a noble gas or octet configuration. The elements that are involved in this trend are sodium, magnesium, and aluminum, which exists as a metal. Silicon. Silicon is the metalloid. Okay, remember that when I say that metalloid is the mixture of metal and non-metal. And for non-metal, we have the phosphorus, P4, sulfur, S8, Cl written as Cl2, and the last one will be argon. So this will be known as the non-metal. So why do I write the phosphorus as P4, the sulfur as S8, and the chlorine as Cl2? Why don't I just write it as P, S, and Cl? This is because this three element, you must write it as is in stable state. So in stable state, this phosphorus, sulfur, and Cl2 will exist in this molecular formula. Okay, so make sure you remember these three, right? For the elements sodium, magnesium, and aluminium, so they are metal, so they will have the bonding as metallic bonding. So metallic bonding is directly proportional to the number of valence electron. So for sodium, it is in group 1, so it has a valence electron of 1, followed with magnesium 2 and aluminium 3. So I've already said that metallic bonding is directly proportional to number of valence electron. So means that aluminium would has the strongest melting point and boiling point between magnesium and sodium. So we're gonna arrange that aluminium followed with magnesium, which is stronger than sodium. For the silicon, which is our metalloid, it will has the covalent bond where it will form a gigantic molecular structure. So how does it form this structure? It is when each silicon atom, so this green silicon, is bonded tetrahedrally. Tetrahedrally means bonded to another 4 silicon atom, which is the red one. Okay, so what does it mean by bonded tetrahedrally? Means this green silicon atom will bonded to another 4 silicon that is red in color. Okay, and this red silicon, okay, will bonded to another 4 blue silicon. Okay, so this thing will extend more and more. So that's how it's gonna form a gigantic structure. Okay, so we don't have to compare the metalloid to any other. So the last one would be the phosphorus. So these are non-metal. So they will have the van der Waals forces, or in the short form of VDW. So van der Waals forces is directly proportional to the molar mass. So you have to calculate all the molar mass for phosphorus. Remember that it should be written in P4, sulfur in S8, and Cl2 in SCl. So the molar mass would be 60, 112, 34, and 18. Okay, so the highest van der Waals forces mass has the highest molar mass, which is the S8. So we're gonna arrange the non-metals stronger than P4, stronger than Cl2, stronger than argon. So the last thing that you have to know for the metallic characteristic is you should be able to arrange all of these elements from sodium to argon in order of strength of attraction. So the strongest bond would be the metallic bonding, followed with covalent, and the weakest one would be van der Waals. So the element should be arranged in a way that aluminium has the strongest attraction. The middle would be the silicon for covalent bond, and the van der Waals. Okay, you just write it in the order that we have written before. So if the question asks you, okay, how does the strength of attraction decrease? So it will go from metallic to van der Waals process. Okay, so that's all for the metallic character.
The last thing in chapter 3 is to know the oxide of period 3 elements. So for the metal, sodium, magnesium, it will form a basic oxide. Okay? Because when sodium reacts with H2O, it will form sodium hydroxide. So this hydroxide, which is the OH minus, it exists as a base, right? So sodium and magnesium will form basic oxide. For the aluminium, it would form amphoteric oxide. What does it mean by amphoteric? It can act as both acid and base. For the non-metal elements, it will form acidic oxide. They are acidic oxide because for example, when phosphorus reacts with water, it will form phosphoric acid, okay, which has a H plus in it. Okay. H plus has an acidic character, so these are the acidic oxide. In short, in order to determine the oxide of period 3 element, you have to write the equation between the metal, the amphoteric, and the non-metal reaction with water first. And then you have to figure out whether OH minus or H plus is being produced. Okay? If OH minus is produced, then metals, the sodium and magnesium will form basic oxide. And for the non-metal, okay, it releases hydrogen ion in the product, so they will form acidic oxide. Okay, for amphoteric, it depends on your equation. If you want the AlO3 to be base, then you have to react with acid. But if your AlO3 is an acid, then you have to react with a base. And the product and side product would be different as well.